What's this question? The question is this: they are giving the page size, and PTE means page table entry. So it is the page table entry size is given, and then they are talking about the outer page table size. So if you have many levels, then they are talking about the outermost page table. Okay, so outermost page table is nothing but the first one, which will be accessed by the CPU, and innermost page table is nothing but the last one, which will point to the pages of the process. That is the convention. Okay, outermost means the one which CPU will access first, and innermost means the one which is directly close to the process, right? And they are saying that outermost page table is so and so, and number of levels used in the paging are so and so, and then they are asking you what is the address space of the virtual address space size. Virtual address space or logical address space, both are same. See, in all the questions wherever I have used virtual address space, you could have even replaced them with logical address space, and you could do the same thing, right? So they are saying that outer page table size they are giving it. Why should they give the outer page table sizes? The only page table which will not completely fill a page is the outermost page table, right? And in the next level page table we are see, why do we go to the outermost page table? Only when the inner page tables are not small to be fit in one page. So whenever at any level we have page tables so big that they don't fit inside the one page, then we are going to divide into various pages, and we are going to go for the number of levels, and always the number of levels will be equal to the how many levels will we generally have is, we generally go till the last level, where the last level page table is going to fit in one page. And sometimes what happens is, the last level page table might say that I don't require the entire page. Then in that case the page table size and the page size might not be same. That is why, see this, in the last level page table, watch it, if the page size is 4 KB, it so happened in this example that outer level page table is 4 KB, right? And the last level, the outermost level page table cannot have more than the page size. The reason is, if it is greater than the page size, then we go for one more level, so that at least that level page table will fit in one page, right? So we are going to do the number of levels, or the page tables will be broken into number of levels until the last page table is going to fit in one page. Remember that, okay? And now they are asking what is the size of the virtual address. And then in order to solve this, one more assumption is given. Assume that except the outer level page table, which means the last one, except that all the pages of the inner page tables are completely full, which means except the last one, which might not be completely full, and in some cases it will be completely full. All the inner level page tables are having pages, and all the pages are completely full. That is the assumption, right? So I hope that you have understood the question. Okay, I'll solve all these questions. Maybe by the time I finish solving them, you'll understand it. Watch it. Now, what I mean to say is, see, outermost page table is containing, okay, see this first one, page size is 4 KB and page table entry size is 4 bytes, and outermost page table is 4 KB, and the number of levels is 1. So when you have only one level of paging, how is it possible? One level of paging is possible only if there is a page table in the first level itself whose size is less than or equal to the page size, right? So whenever page levels, levels of paging is 1, then there is only one page table, which is nothing but the outermost page table. So in this case we have only one page table, right? And the page table size is 4 KB. Page table size is 4 KB, right? We have only one page table, right? If the page table size is 4 KB and page table entry size is let us say 4 bytes, then how many entries will be there? The number of entries in the page table will be 1K. 1K entries will be there, right? So what happens now? If I have 1K entries in the page table, then it means that the number of pointers that will come out of each entry is 1, right? So all the pointers coming out of this will be 1k, right? And every pointer is going to point to one page, right? So if I have these many entries coming out of the page table, then the number of pages in the process is nothing but 1k. So 1k pages are present in the process, right? If 1k pages are present in the process, and if size of each page is 4kb, then what is the size of the entire process? Size of the entire process is 4MB, which is nothing but virtual address space. Got it? So virtual address space is 4MB. Understood this? So there is only one level paging, and the page table size is 4kb, and the page table entry size is 4 bytes. Therefore the number of entries present will be 1k, and so 1k pointers will come out. Each pointer will point to one page of the process directly. The reason is there is only one level of paging, therefore the number of pages in the process are 1k. If the number of pages in the process are 1k and the size of each page is 4k, then the total size of the process will be 4MB. Got it? That is why I got 4MB. Now look at the next one. The next one is saying that in the next one, two levels of paging are used. So whenever there is two levels of paging, then there will be outermost page table that will point to the pages of the inner page table, and that inner page table will point to the pages of the process, right? Watch it like this. Now there is outermost page table, right, whose size is 4kb. Watch it, because they have already told that the outermost page table size is 4kb, right? Therefore the outermost page table size is 4kb. If the outermost page table size is 4kb and the size of each page table entry is 4 bytes, then how many entries will be there in the outermost page table? The number of entries will be 1k. Therefore how many pointers will come out of this? 1k pointers will come out of k pointers, right? And now each pointer is going to point to a page of the inner page table, right? It is not the process, inner page table. If k pointers are there, then how many pages will be there in the inner page table? K pages will be there in the inner page table, right? And again, you remember the assumption? The assumption is that every page in the inner page table is completely full, right? And we know that the page size we already know it, right? How much is page size? 4k. Each page here is of size 4k, and again each page here is of size 4k, and page table entry is 4 bytes. How do you know that the inner page table size is 4 bytes? At any level the page table entry size is same. The reason is every level is going to point to the frame number, right? So at every level every page table is going to point to one of the frames. Therefore all the page table entries are always same. So now how many entries are present in each page of this level page table? 1k entries. So how many 1k entries will be coming out? So how many pointers will come out here? Totally I have k pages, and every page is going to give out k entries. Therefore the number of entries coming out will be k square entries, isn't it? Or you can think of it like this. Or how many entries will be coming out from each one? Totally k into k entries will be coming out, right? And there is only two levels of paging. First level is over, second level is over, and finally each pointer will be pointing to one page, right? Each pointer will be pointing to one page, and these pages belong to the process, right? So how many pages are there in the process? The total number of pages present in the process are k into k pages, right? And if these are the total number of pages present in the process and size of each page is 4kb, then what is the total size of the pages process? See, k into k process are present in the process, k into k pages are present in the process, right? And then size of each page is 4kb. So 4kb is size of page. Therefore what is the total size of the process? Total size of the process is 4GB, right? Fine. And now next one is 3 levels. So 3 levels can be expanded just this way. See this? 4kb page is in the size of the outermost page table is again same, 4kb is given, and the page table entry is 4 bytes. Everything is same except that there are 3 levels of paging, right? So first level is going to give out 1k pointers, and all these pointers are going to point one page each of the second level pages, right? Okay, so first level, second level, that that depends on the question. So here I am assuming that it is the first level, or okay, let's say this outermost, second outermost, third outermost. Let's go that way. So outermost page table is going to give us k entries, and therefore the number of pages which are present in the second outermost level page table is k, and each page of the second outermost page table will give out again k entries, and they will point to the third outermost or the innermost page table. Therefore, how many pages are present in the innermost page table? K into k pages, and again each page size is 4 KB and the page entry size is same. Therefore, how many pointers will come out of each page of the innermost page table? Again k, right? Each page. Now there are k into k pages, and each page is going to give out k entries or the k pointers. Therefore, totally how many such pointers will be coming out of this? Here k into k, right? So finally the process is going to contain the number of pages which are equal to k into k. Therefore, our process is going to contain k into k number of pages, and the page size of each one is 4 KB. Therefore, the total virtual address space is going to be 4 terabyte. Got it? I hope that you understood this. So if you didn't understand it, please watch it again, you'll understand it. Okay. And next question is same. 4 KB is the page size, and page table entry is 4 bytes, but only difference is the outermost page table is containing only 256 bytes. See, that is the difference. Outermost page table might not completely fill up one entire page. It so happens that in many cases that the outermost page table might fail to fill up the entire page or might occupy a small portion of the page. Even then you should not say that it is waste, and you should not try to eliminate it. It is required. If you don't have that outermost page table, then the inner page table might contain many pages and they will be spanned over many frames, and it is very difficult to keep track of everything. Okay, why is it so important that the outermost page table occupies only one page? Because if it is fitting in only one page, that can be loaded in only one frame, and CPU can load in one of its register what is that frame address. If the page table doesn't fit in one page, then what happens is that page table has to span over many frames, and CPU has to now keep track of where all these frames are. So it is better that you have one page and one register, so that CPU will remember where that page is. Now once you get into that page, it will be easy for you to find the frames of the inner pages. Got it? That is how it works. Now watch this. The next one is saying that page size is 4 KB, fine, and the page table entry size is 4 bytes, fine, but the outermost page table size is 256 bytes, which means the outermost page table is less than the page size, but still we have to go with this, right? And now let us say there is only one page, one level of paging. If there is only one level of paging, there is only one page table, and that is the outermost page table. So in this condition, what the problem becomes is there is only one page table, right? And whose size is 256 bytes. The page table size is 256 bytes. There is only one page table, right? So if the size of the page table is 256 bytes, and if the size of each entry is 4 bytes, then how many entries are present in this page table? It is 2 power 8 divided by 2 power 2, which is 2 power 6, which means 64 entries are present in the page table, isn't it? Therefore, how many links are coming out of the page table? 64 links are coming out, and each link is going to point to one page. Each link is going to point to one page. Therefore, how many pages are present here? 64 pages are present here, right? And since it is only single level paging, directly this page, there will be only one level of page, and then that page will directly refer to the pages of the process. So what will be the size of the process completely, or size of the virtual address space? Virtual address space size is 64 pages, right, into size of each page. Size of each page is 4 KB. So what is 64? 2 power 6. And what is 4K? 2 power 12. Therefore it is 2 power 18 bytes, which is nothing but 256 KB. 256 KB. Got it? Right? Okay, let me check it once. See, 256 bytes is the total size of the page, and therefore the number of entries in the page will be 64. Fine. And therefore number of pointers coming out of this one is 64, and each pointer is going to point to one page of the inner page table. Therefore how many pages will be present? Yes, 64 pages, and therefore size of each one is 4K. Yes, that's it. And next one is saying that there are two levels. With the same one, there are two levels of paging, which means if there are two levels, the first level is page table and second level is also page table, right? And in the second level, each page size is 4 KB and the entry of each one is 4 bytes. Therefore how many entries will be present in each page of the inner page table? 1K entries. So from each one, K entries will come out, right? So if you put them all together, right, there are 64 pages, and from each one 1K entries are coming out. So how many total entries will be coming out in general? Therefore it is 64 into K entries will be coming out, and each entry is going to point to a page. And in this case, since it is only two level paging, right, and all the two levels are over, the final level, this level will contain the process, right? So how many pages will be present here? Since 64 into K entries are coming in, right, therefore the number of pages present in this level are 64K pages will be present in the process, and the size of each page is 4KB, right? Therefore the total size of the virtual address space is, you can fix it. So how much is this? 2 power 16 into 2 power 12. So how much is this? 2 power 28 bytes. So which is 256 MB. Right? And what about the next one? So the next one is page size is 4 KB and page table entry size is 4 bytes, and the outermost page table is 256 bytes, right? I mean, yeah. So they are saying that only thing is three levels of paging are possible. If three levels of paging are possible, see, first level of paging, second level of paging, third level of paging, and this is also a page table, right? And how many pages are present in this page table? We have already seen it. The number of pages present in this page table are 64K pages, right? So 64K pages are present, and each page will give out 1K entries, right? Therefore in the next level, how many pages will be present overall? 1K entries, and each entry is going to point to one page. Then how many pages will be present in this level totally? It is 64K into 1K pages will be present here, right? Therefore the total number of pages present in the process. Why am I calling it as a process? Because three levels are over: first level, second level, third level, right? Therefore it is 64K into K, right? 64K into K pages are present, and the size of each page is 4KB. So this is the total size of the process here. I mean, yeah, virtual address space. So how much is this? 2 power 16 into 2 power 10 into 2 power 12. So how much is this one? I think if you add it, it will come to across 256 GB. So 256 GB is the size of the virtual address space, right? See, and one more thing, if you observe the way I did it, the same way we did it for, decoders, multiplexers, right? As well as we are going to do the same thing for even the trees, B trees, B plus trees, everything, right? So we did it in the same way. Even we will do it in other subjects as well, B trees, B plus trees, everything. But anyway, this expansion is straightforward. Okay, I hope that you understood it. If you didn't understand it, you please watch it again and again. So points that you should remember here is there has to be paging until the last level page table is going to fit in one page. That is first important point. And second thing is, generally the inner page tables will all be completely full except possibly the last page. the last page might not contain the complete or might not be completely full. Except the last page of every page table, all the other pages have to be completely full because we don't want to waste the memory. Got it? Okay, here I solve this under the assumption that except the outermost page table, all the inner page tables or when divided into pages, every page of the inner page table is completely full. Under that assumption I solved this and I got these answers, right? Okay.